Okay, so let's start with the just some recap of what we did yesterday. For those of you who didn't come yesterday, didn't join us, don't worry, I'll upload the YouTube live video. Sorry, not YouTube live, just a recording on YouTube. And then what we've done yesterday is we have figured out how to move a spacecraft from the orbit of the Earth into the orbit of Mars. So what we have done yesterday is we figured out how to do a Hohmann transfer ellipse. I give you some the plan already, how to design such transfer orbit. And then we've looked into the hyperbolic orbit around Earth, okay, and how to design that launching opportunities, launching trajectories and everything. So we've done those two. So now we need to look at, when we arrive in the orbit, what do we have to do in order to actually park ourselves in this orbit. Okay, so when you launch from Earth into Mars, you have three options. One is to actually hit the planet. Let's say you are launching a rocket, a guided missile, something like that, interplanetary missile. You can do that. You can launch it from Earth and then make sure that it hits the planet when it arrives here. Okay. Option number two, which is what we are going to do today, because we are a peaceful galactic being. We want to actually send our spacecraft so that it orbits Mars. Okay, so that's what we're going to do today. Another thing you can do is actually what we call a flyby. You launch spacecraft from Earth, okay, you launch from here, and then when it arrives here, you don't park yourself here, but you use the gravity of Mars to go somewhere else. Okay, so you launch here, going to Hohmann transfer ellipse. When you arrive here, you don't park yourself here, but you use the gravity of Mars to get yourself into another hyperbolic orbit to launch yourself to some other place. Okay, so that is what we call planetary flyby, or we can call it gravitational assist, which means we are flying in space using assisted by the gravitation pull of a planet. That's gravitational assist. Sometimes this is also called gravitational catapult, because basically what we are doing is we are trying to find some help from the planet, its large gravitational pull, to push ourselves into, catapult ourselves into another trajectory. So usually that's being used to go somewhere far, far away. For example, New Horizons spacecraft use that, multiple flybys to get into Pluto. The one we see yesterday, the Rosetta mission, they also use multiple flybys to get into the comet. It took them 12 years to get into the comet, but we are looking into something that is more, I think, is shorter, a relatively simpler maneuver. We just want to launch from here, arrive here in an orbit. Okay, so this is just a recap what we've done yesterday for Hohmann transfer ellipse. Make sure you use the right mu. Okay, and this is, I think, pretty easy. Delta V1. Notice that I use small v because this is actually the delta V, the the heliocentric speed. Okay, so delta V here is the heliocentric speed. Okay, all right. So now we have departed from Earth. What to do when we arrive in Mars's orbit? So this was the question yesterday. So as usual, we are going to get we are from an hyperbolic trajectory. What we want to do is get into the parking orbit. Okay, see. Oops. Alright. What's the animation? Didn't work. Maybe we try this. Animation pane. Okay. Alright. So we have established delta V2 from before. So spacecraft is gonna go there and then make another delta V here at this point right here. Okay. This point, so that it can get into this orbit. If it doesn't stop here, then it will go into a what we call just now a flyby trajectory, gravitational assist maneuver, gravitational catapult. If you don't stop here, but we are going to stop here and park around Mars. So we need to do another delta V here. We call delta V here delta V arrival. Before we have delta V departure, which if you note is different from delta V1, delta V departure, and then now delta V arrival. Okay, so basically we establish injection near the surface of Mars from a hyperbolic trajectory, this one, into an aerocentric, sorry, not aerocentric parking around the orbit. Aerocentric meaning an orbit centered focused in Mars. Geocentric will be orbit focused in on Earth. Heliocentric will be orbit focused on the Sun. Aerocentric will be focused on Mars. Okay, Martian parking orbit. So that's what we're gonna do. Now we need to figure out the same thing what we've done before. We need to figure out what is the basically what is the delta V here, and then where to put it. Okay. So the way I want to do it is I want to do it like a problem. We start with a problem and then we try to find to solve it, instead of giving you all the formulas to solve it and then give a problem. Let's do it different way. The problem here is this. Say we want to park the spacecraft on an aerocentric orbit around Mars with a period of 7 hours. Okay, I don't care if it's the parking orbit is elliptical or it's a circular orbit, doesn't matter. Okay, so just to not confuse you, let me make some weird shape here. Okay, all right, there you go. Okay, it doesn't have to be a circular orbit, it just have to be a parking orbit with a period of 7 hours. Okay, now we need to find these 4 important things. Obviously, what we've done so far for orbital maneuvering is to find delta V. So what is the delta V here? Well, what do we need to do here? Okay. Second thing is, where do we want to do this? So to answer where, we need to find the radius of perihelion. In other words, the periapsis of Mars, perihelion, radius of here. If on Earth we call it radius of perigee, right? So on Mars we call this radius of perihelion. And then we need to find, obviously, where should the delta V occur? What's the angle here? You coming in, where do we need to do our delta V? So that position is also denoted by angular distance beta here. And then the aiming radius delta. I'm sorry I have to use delta again, not to confuse you, because we are using so many Greek letters and Roman letters, so we need to actually do this. Delta is actually, okay, it's the distance between this line here, the line, asymptote line of the hyperbolic orbit, into, sorry, not that. I think I have a better figure here than this one. Oh, here, aiming radius. Okay, so the distance between the asymptote line of the hyperbolic orbit onto the whatever we want to do it. Okay, so in this case our aiming radius is this. So aiming radius in our case is this. Okay, I couldn't get it too straight. Yeah, that is our aiming radius. Okay, if your aiming radius is too big, you're gonna hit the Mars, you're gonna hit the planet. See, if your aiming radius is this, then what you're gonna have, what's going to happen is you launch your spacecraft coming in from a hyperbolic orbit, it will just crash on this one. You don't want that to happen. You love your spacecraft, you spend billions on it, okay? So you want to make sure that the aiming radius is follows the radius of perihelion that we've decided before. Okay, so that's aiming radius. I think I need to actually save this one. All right, so that is our mission. That is our problem. Okay, you stare at the figure first, and then let's see if you have any question on that one. Stare at the figure first. Yeah. Yes, Lee. Abdul Rahman, what's going on? V infinity so straight. V infinity, okay, macam mana boleh curve? Okay, if you remember, here, that's a good question. Let me see if I can find the picture of our hyperbolic trajectory. Okay, all right. Okay, so let me paste it here. Okay, so if you can see this, okay, the question Lee was asking is, why is velocity infinity, v sub infinity, is so straight? The reason is that, let me make sure. Okay, the reason is that we assume that the velocity when they're coming in, it follows this asymptote line. So you imagine this is the blue line is your hyperbolic orbit. Okay, when you're coming in, usually from far away, it resembles a straight line. Okay, so that's why I draw a straight line to denote the velocity vector of v sub infinity. Okay, but why does it curve? Because you have Mars here. Mars have some gravitational pull. So what's going to happen is going to bend. This is going to bend the trajectory because of Mars gravitational pull, and then follows the hyperbolic trajectory. Okay, so if, for example, if you're asking, let's say Mars doesn't have any gravitational pull, it's empty inside. Empty inside. So it doesn't have any mass, it doesn't have any gravitational pull. So what's going to happen is the rocket is going to just go straight line to I don't know where. Okay, but because the Mars have a gravitational pull, it comes in straight, but it's going to get tucked in by Mars's gravitational pull and resulting in hyperbolic orbit. I hope that answers your question. Actually, that's a brilliant question. Okay. Yep. Okay. Also note that these dotted lines are imaginary lines just to show you the geometry. But in actuality, hyperbolic orbit will be like that. So this line, horizontal line right here, is the the asymptote line. That means if you go far away, then this trajectory is gonna coincide with this horizontal line. Okay. Let me see if there's any other questions. Okay. All right. So another question you might ask, okay, why is it not coming from the left-hand side, but on the right-hand side? Okay. The reason is this. Okay. When from Hohmann transfer, the spacecraft coming in is actually slower than Mars. I repeat that again. If we do a Hohmann transfer from Earth to Mars, at the end of the Hohmann transfer, the velocity is going to be a bit slower than the Mars orbital velocity. Okay, but opposite happens when you go from Earth to Venus. If you go from Earth to Venus or any inner planet, you have your arriving speed is actually much greater than Venus. Okay, but in this case we are moving out towards out. The speed is actually less than Mars orbital velocity. So that's why if you're coming in from this side, you're not going to catch up with Mars because it's much speedier than you. Okay, so usually for illustration purpose, I will do it this way. I will say that the velocity, the spacecraft is coming in from the frontal area. Okay, it's like this. So it might be confusing if you look at it in a bigger scale, but usually a lot more complicated things happen in space. But here, let's just assume, to simplify the situation, simplify our analysis, which is a patched-conic approximation. We say that the spacecraft is coming in from the front side of the sphere of influence. Okay, so this is how I draw it. I think if you look at Curtis' book, I think also explains that. I think Curtis' book explains that as well, if I can find. Oh, here, yeah. In the case illustrated in mission from inner planet 1 to outer planet 2, example from Earth to Mars, the spacecraft heliocentric approach velocity is smaller in magnitude than of planet Mars. Therefore, it crosses the forward portion of sphere of influence. Okay. Right. So, if you are going from outer planet to inner planet, Earth to Venus, for example, then spacecraft must cross the rear portion of the sphere of influence. Okay. All right. So don't be confused with this one. I think it for our analysis purpose, the geometry is correct enough. Okay. I'm trying to use the same nomenclature here, because if you use the Dept, White, and Mueller, I think they use different. Nomenclature. I think they use Y to represent delta, the missed distance. Okay. Sorry. So yeah. Okay. Let me see. Oh, in Dept, Mueller, and White, fundamentals of astrodynamics, it doesn't show where the planet's velocity vector. It just shows this. Like I said, for illustration purpose, this is good enough. So just like Dept and Mueller and White, I think they just simplify everything, just draw the diagram like that. Okay. So hopefully you're not confused with that one. So yep. There we go. So let me stop if you have any questions. Okay. Just a few seconds. Just stare at this. I'm giving you a few seconds just to stare at it and then ask any questions. Someone's trying to talk, because if you're trying to talk, then I cannot hear you because your mic is problematic. If not, then I will continue. Okay, I will continue. Now, okay, so we are arriving on Mars. We are coming in from a hyperbolic trajectory. We want to park ourselves into an orbit here. What's the characteristic of the parking orbit? It's just, it has a period of 7 hours. Okay, nothing else is given. A is not given, E is not given. Okay, we need to park there. If we don't park it here, then we're gonna just whew. Okay, so 4 things we need to find. Delta V arrival here. What's delta V? What's the change of velocity that we need to do here? What's amount of fuel that we need to do here, expand here? Okay. And then radius here, radius of perihelion. the aiming radius, which is where is it? The aiming radius. Okay, so that you actually arrive at the parking orbit and not hit Mars or go too far away. And then finally the angle beta. Okay, let's do the first thing first. There are a few formulas here. Not many, 5, maybe 6. Okay, so let me just give you the formula first. The minimum delta V arrival, how you want to find it is using this formula right here. Okay, I don't want to spend time during the derivation, but I think you can find it in Curtis textbook. Okay, so that delta V arrival is equivalent to V infinity square root of 1 minus E divided by 2. So now we don't know these two, V infinity and also E. How to find that? So similar to departure maneuver, okay, like what we've done before, the arrival maneuver assumes V infinity is equivalent or approximated to delta V2. If you remember from our departure maneuver also, V infinity is equivalent to delta V1. Okay, that V infinity is different from this V infinity because remember we are doing this conic right now, conic orbit. Okay, we're not doing this anymore. So V infinity here is different from V infinity here. Okay, how different? I've already given you this. Okay, delta V1 and delta V2. So this one is for departure. We don't care about that anymore. Throw that away. We only care about this arrival. Okay, delta V2 here. So we can assume how to find how to find V infinity is I just use the same formula. Okay, for delta V2. Clear. You know this. You can find it. You know this. R Mars. Remember, yeah, R Mars is not the radius of Mars. It's the distance of Mars from the Sun. Same thing as our Earth here. So I don't want you to be confused. Please do not be confused because you're gonna get a totally different answer. Okay. You know what? Let me just put a reminder here again. Okay. Sorry. Our Mars is the distance of Mars from the Sun. Okay, and not the radius of the planet. Okay, let me make sure that oops, what happened? All right, there. Ding. All right, same thing. Our Earth also same thing. So now we found this E. What about E? Eccentricity. So what we are trying to find is the eccentricity of the parking orbit, not the eccentricity of the hyperbolic, but eccentricity of the parking orbit. So you can find this. How do I find this? Okay, there's a condition because we in space we need to save fuel. So in order to save fuel, we need to find a delta V maneuver that uses the minimum fuel expenditure, minimum delta V. Okay, because delta V equates to fuel usage. So you want to always aim for minimum delta V. So if you want to use minimum delta V, then there's a formula for optimal radius periapsis or optimal radius periarion here. I'll give you the condition there. Okay, small thing there because I don't want to interfere with my explanation here. So that's the condition of radius of periapsis such that the delta V here is minimum. Okay, so that means RP is dependent also on the how much delta V you're going to use. Okay, so always do this. If you want to make change afterwards, you want to change into what kind of orbit, whatever, you can always change it later using whatever you used before, delta Hohmann transfer ke by elliptic ke. But when you're arriving for hyperbolic trajectory, you want to get into this orbit, always use the optimal radius of periapsis. because we always want minimum delta V. So this is the formula. Write this down, or better yet, just copy down this PowerPoint slide and then make sure you know it. Okay, so that's it. 2 mu Mars or divided by A V infinity squared minus 1. Okay, we know this, we know this, we know this, we know 1, we don't know A. What happened? Okay, we don't know A. We can find the semi-major axis A of the parking orbit by using the period formula. Right. You remember what is our period of the parking orbit? It's given in the question, 7 hours. Okay, make sure you change 7 hours into seconds, put it in here. But then don't forget, this is Mars. Okay, and then you can find A from using this material. So you find this, find that, put it in here, find this, put it in here. There you go, you got the delta V arrival. Settle. First question. Okay, I'm gonna stop for a few seconds if you have any questions for me. Okay. Oh, Kishore has a question. So far, no that okay. If everyone else is the same, I'll just wait a few minutes, a few seconds. Okay. All right. Now, second question is the radius of perihelion. Radius here. Okay. Just a formula. Okay. This comes from here, optimal radius of periapsis for minimum delta V. Already given it to you there. Okay, same thing. Oh, hopefully it's the same. 1 minus E. Excuse me. Oh yeah, see. You already got E of the parking orbit, yeah, not E of the hyperbolic orbit. Put it in here. We got it. Nice. So now you know where to. How far is it from Mars? You need to apply your delta V arrival. Next is the aiming radius. Like I said before, okay? Now, what happens after crossing the sphere of influence? If you're coming in here, okay, you got 3 options. Okay, if the goal is to hit the planet, then the aiming radius must be really small. No, sorry, really big. Okay, if you want to hit the planet, then your aiming radius here must be, if you want to hit the center of the planet, there you go. That's your aiming radius. Okay. If you usually you don't want to do that because there's no point. We are not in war with the Ravagers or anything. You still remember your EDF, Earth Defense. Okay. We're not doing that, so usually what we do is we're gonna have some kind of aiming radius, which is quite small, for 2 purposes. One is to go to an orbit around the planet, like what we're doing here. Or if there's no impact, or you do not drop into a capture orbit here, this would be called a planetary flyby. Okay, or gravitational assist maneuver. Okay, it's future topics. Actually, the analysis is pretty much the same. If you understand this, planetary flyby is just adding 1 or 2 formulas only. Okay, all right. So this is what I call aiming radius. I use delta because this is what is being used in Curtis handbook. Textbook. If you use the fundamental of astrodynamics, Bate, Mueller, and White, I think they use Y. They use the letter Y. Okay, I'm just gonna be consistent here. Okay, so the formula is this or this, whichever you want to use. Okay, and make sure if you want to use this, then I think it's pretty much given here, okay? But if you already found RP, then you can use this formula right here. Again, this E is the E of the capture orbit, okay, this orbit here. Again, let me redesign this orbit so that you don't confuse that it's not necessarily a circular orbit. It could be an elliptical orbit as well, okay, as long as the period. Okay, so aiming radius formula, so plug and chug. All right, no worries. And then next, we know where to put it, and then at what distance from the planet. Now we need to find the angular position, beta, okay, the position of this periapsis here, position of this periapsis point. Again, it's just simple. We use the formula that we've used before, beta. I think you've already known that from previous departure maneuver analysis. So for arrival maneuver analysis, you use the same formula. Okay, so think of a question, but before you ask, type in your question. But before that, I want to explain why I put here this letter eta here. The reason I put this here is because in the textbook Fundamental of Astrodynamics, they use eta instead of beta. They use this letter here and this angle here instead of beta. So, okay, so I think I gave you a formula before if you have calculated that. Oh, sorry. So, eta is just pi, or maybe you want to use 180 if you want to use degree. Okay, pi minus beta. Okay, that's the formula. Okay, if my trigonometric identities is correct, if I can still remember it, eta can also be this whole thing minus, same thing. Okay, I think, let me check that. Let me check. Big Mueller and White. Does it discuss on eta? Yeah, it does. Actually, I got it from there. Where is it? I thought I found it somewhere. Weird. It's not here. Where did I got it from? Is it from my dream? Oh yeah, there you go. Let me make it big. So in the Fundamental of Astrodynamics book, it uses this angle. Okay, so eta here, if you can see that here, ding 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 ding. Okay, and the formula for eta given is cosine eta equivalent to -1/e, which is the same. Cosine beta is equal to 1/e. Okay, don't worry, 1/e. Let me check again here. Beta. I think this book uses beta. Yeah, here. So beta is, cosine beta is 1/e. Okay, cosine eta is -1/e. Okay, the reason is beta plus eta is 180 degrees. So I was right. Okay. All right. So with this 4 steps, I've break this problem into 4 sub problems. Now you can park yourself in this orbit right here. What you gotta do next is up to you. If you want to change your parking orbit into something a more useful orbit, whatever, it's up to you. So I'll attend to any question that we have.